Section 5.1, Part 2, radians, arcs, and sectors. So radians is another way of measuring angles, which we have learned also to use degrees. So we started with degrees, and now we're going to talk about radians today. And radians is what we're going to deal with mostly in trig, because the conversions make it the easiest equations and easiest methods to use. And if we use degree, those conversions and formulas would be much more complicated. So that's why we can take a degree, convert it to a radian, and therefore use the much simpler way of calculating parts in any trig unit. So we're going to start with the definition of a central angle, which is an angle whose vertex is at the center of a circle. So if I created an angle and its vertex is at the center of the circle, the origin, which it is, then this degree is what we could call a central angle. Circle arc is a segment of the circle's circumference. So, using that central angle, I could say this part of the circumference is known as the circle arc. And we are going to label that as S. And then the word subtends means to create, it creates or fixes. So in the picture above, we would say that S subtends our theta. Or we could also say that theta is subtended by our circle arc S. So basically we're saying that a circle arc creates our degree. So if we have an arc on a circle and we take that piece and make a central angle from it, because it made it from the circle arc, we say that the circle arc subtends our theta, our central angle. So the definition of a radian is if the central angle theta is subtended by an arc that is equal in length to the radius, then that theta equals 1 radian. So again, if the central angle theta is subtended by an arc that is equal in length to the radius, then theta is 1 radian. So then how many radians would be in one circular revolution? Well, we know that arc length has a formula, which is S equals our radius times theta. So for a full revolution then, our arc length equals the circumference. And again, that's because it's a full revolution. So therefore, we know that circumference is 2 pi r. So now we can say, well, if they're equal, then we have r, our radius, times theta, which is equal to 2 pi r, which is our radius. And since we have r on both sides, those can cancel. So now our theta, our degree, therefore equals 2 pi. Now I said degree because that's what we're used to the central angle being, a degree. But now theta is in radians. So one whole circumference has a radian of 2 pi. So again, all the way around this circle is 2 pi. So now if I want half of that, Well, 2 pi divided by 2 would be pi. If I want a quarter of it, I half my half, so I have pi over 2. Then if I want a sixth of it, that would be pi over 3. Because we would have 2 pi divided by 6, which is 1/3, pi over 3. So it is important to know how to convert from degree to radian and radian degree, because you might be given one but need to work with the other and vice versa. So we know already, though, that 2 pi is 360 degrees because it's 1 revolution. Well, we also know that pi is half of a revolution, so that's 180 degrees. And then a quarter of a whole revolution, we know, is 90 degrees. So I would say the top row there you could do logically, because you know what a 90 degree and 180 and a 360 angle looks like. But when we get to this bottom row, it gets a little bit more complicated. So since I'm given radians, I'm going to convert by multiplying by 180 over pi, because I want a degree. So I choose that conversion because I need to multiply it by something that's going to cancel out my pi, because I no longer need pi in degree. So in your calculator, you just do 180 divided by 3, and you get 60. Same thing over here. Pi over 4 times 180 over pi. 180 divided by 4 is 45 degrees. And our last one is pi over 6 times 180 over pi, and we would have 30 degrees. So now we're going to convert. Number 1, we have a degree and we need to go to radians. So to do that, we're going to start with our degree and we're going to multiply it by the other conversion factor, pi over 180. And I know that I'm choosing that one because that gives me a pi left over in my answer, which all radian values have pi in it. So you're going to do 50 divided by 180. In your calculator, you can do math frac, and you're going to get 5 over 18, and then we add our pi in, 5 pi over 18. So I'm actually going to go do number 3, since that's also in degree. I'm going to have 160 times pi over 180. The fraction of 160 divided by 180 is 8. Add in the pi over 9. Now we have degrees, so we're going to go back to 180 over pi. So we have negative pi over 9 times 180 over pi. Pi's cancel. 180 divided by 9. Actually, negative 9, because there's a negative right here, is going to give me negative 20 degrees. And then, if I have 5 pi over 6, I'm going to multiply it by 180 over pi. Pi's cancel. But now I have 2 numerator values, so all you're going to do is 5 times 180, and then divide it by 6, and you get 150 degrees. Okay, so now we're going to recall coterminal angles, and we know that those are 2 angles that have the same initial and terminal sides. So, to do coterminal but in radians, instead of 360, we're going to add and subtract 2 pi. So, I want one positive and one negative that's coterminal with pi over 4. So, here's my positive, pi over 4 plus 2 pi. So technically, I'm taking 1/4 and I'm adding it to 2, and then you have a pi left over. So you can do these things in your head with fractions and things like that. So the first step that I would need to do is find a common denominator. So 2 pi would become 8 pi over 4. So pi plus 8 pi is 9 pi over 4. Now, the negative one is the same thing, except I'm going to subtract 2 pi. Again, I need to convert, but now we have 1 pi minus 8 pi, which gives me negative 7 pi over 4. Okay, so now that I have a I need two angles that are coterminal with negative 2 pi over 3. So I start with negative 2 pi over 3, and I'm going to add 2 pi. So hopefully it makes it positive. If it doesn't, I'll have to add another 2 pi. So to find a common denominator, I will have 2 pi over 3 plus 6 pi over 3. And then negative 2 plus 6 is a positive 4, so we have 4 pi over 3 as my positive coterminal angle. And then negative 2 pi over 3, and we're going to subtract another 2 pi. So negative 2 minus 6 is negative 8 pi all over 3. So that's my negative coterminal angle. Now we know again that arc length is the part of the circumference of a circle. That's very similar to when we just talked about the circle arc, which was a segment, but now it's like the actual length of the circumference. And so now we're going to define sector. So sector is a region bounded by that arc, so it's going to be a region, meaning area, but only part of the area of the circle. So if you look at our little diagram to the right, if I have a central angle like such, that's theta, and therefore I have an arc length, which is all the way like that in green, so that's S. And then I know that my radius is right here. So again, just to confirm in radians, and then our sector is going to be this area right here. So you see below the arc length and area of a sector formula, and then again, note that theta must be in radians. So anytime you deal with r, just think r, which represents radius, like I drew up above. But anytime you see radius, think radians. It has to be in radians. So here's a problem. Find the arc length of an area of a circular sector formed by a central angle of 2 pi. So it's already in radians. That's great. If the radius is 6 feet. So I want the arc length. So first, I'm going to have S equals R times theta. And since we don't know our arc length, so we're solving for S, so we have R, which is our radius, so 6 times, and then our theta, which is in radians, so all we have to do is multiply, and we have an arc length of 4 pi, and then that was talking about feet. Now for the area, that is 1/2 r, r squared times theta. So we have 1/2 times 6 squared, and then our theta is 2 pi over 3. You can help yourself by simplifying in your head by canceling out these 2 since everything is being multiplied. So you would have 36 over 3, which gives you 12 pi feet. So feet squared. So just note that your pi's aren't canceling out when doing this, so it's part of your answer as well. Okay, so now I want to find an arc length that subtends a central angle, so it creates a central angle of 120 degrees. So the first thing I'm going to do is take 120 and convert it into radians. So we have 120 times, so since I need pi, that's going to be in the numerator, and 180 is going to be in the denominator. So my new theta is now 2 pi over 3. So that's just a little extra work since we were given it originally in degree. So for arc length, we have S equals R times theta. So S is going to be equal to our radius, which was told to us, which was 5, times that new radian theta. And we have an arc length of 10 pi over 3. Okay, our last problem for these notes. You have an area of a circular sector within a circle of a radius 3 centimeters. So the area of it is going to be 24 centimeters squared. Determine the size of the central angle of the sector along with the arc length. So we know that R equals 3 and area equals 24. So we just want to say that to pull it out of the problem. So I need to find the central angle, so I need theta, and I can find that because I know the area. So I have 24 equal to 1/2 times my radius, which is 3, squared times theta. So square 3, you get 9 divided by 2. You divide that by the other side, which is 24. So theta is actually going to come out to become 16 over 3. So now we need to find the arc length, which is S equal to radius times theta. We were given S as 3, and we just found our theta. So our arc length is 16, and we're talking about centimeters. So we found our arc length, and then the size of the central angle